Primary resistor reduced voltage starter calculations. In this presentation, we're going to be looking at the inrush current, starting torque, the current on the line and load side of the starter, voltage, line and load side of the starter, and the overload sizing for a primary resistance reduced voltage starter. Now, in order for us to calculate some of these values, we need to work with a motor and have the values of this motor being operated as full voltage to start from. Now, you'll notice that this information here is the same as what we have used for the other reduced voltage starters and the full voltage starter tutorial calculation. If you're unsure of how I got these three values, go back to the full voltage tutorial and it will take you step by step through the process. Now, this motor is going to be used with a primary resistor starter rated for 75% supply voltage. Well, let's first take a look at this starter and the voltage that it is going to apply to the motor. So as a simplified diagram, I have this primary resistor at start. We're applying 600 volt line and we have a resistance in there, which is set for 75%. In order for us to calculate the voltage applied to the motor, we're going to take the line voltage and multiply it by the percent given. We're not going to be using the resistance value and calculating it this way. Now we have 600 volts times 0.75, meaning the voltage across the motor itself is a line value of 450 volts. The starting current of this motor is going to be using the starting current at full voltage times the percent that's given by this primary start resistor. That means that 134.7 will be multiplied by 0.75, giving us a starting current of 101.02 amps. When we look at the torque value for a primary resistor starter, the torque value is going to be calculated based on the percentage, but squared. And that's because the torque will vary to the square of the current change within the motor. So we take the starting torque of a full voltage motor or full voltage started motor, and we multiply it by the percent squared. And what this ends up doing is showing us that it reduces the starting torque by a significant value. We end up going down to 125.88 foot-pounds of torque. Now let's take a look at the current on the line and the load side of this motor starter. If we look at the current on the line and the load side for primary resistor, on start, the current value that we should be expecting is exactly the same on both sides of the starter, 101.02 amps. During run, exactly the same value of current should be present on both sides, and that would be the FLA of the motor. If we look at the voltage of this motor on the primary resistive start, the voltage should be slightly different when we're looking at the starting value. And the starting, we should see 600 volts on the line side, and then the reduced value on the load side, so 450 volts. During run, the full voltage should be applied to both sides, so 600 volt on the line, as well as 600 volt, why does it say 450? 600 volt on the other side. Here, why don't I just correct that while we're going through? There we go. Much better. What about the overload then? Well, the overload is always based on the value of current that is flowing through the overload heater itself. On a primary resistor starter, there are three overloads, and those three overloads sit in the line conductor for the motor. Now, this means that it has the FLA running through it during run condition, and this is exactly the same value of current that we would expect for a full voltage starter. This means the overload is sized exactly the same as a full voltage starter. And it means we take our 27 amps and we multiply it by the multiplier given in 28306, which for this motor is 1.25, giving us a large or a maximum size of overload of 33.75 amps.